transforming sine and cosine functions. So in the previous video, I introduced you to the sine and cosine functions, and my assumption is you're kind of in grade 11 and you're studying these different functions. I'll put up a link up above there to that introduction. Now, once you know how a sine and cosine looks like, and you understand that it's periodic, so it has a particular cycle, and then it just keeps repeating over and over, has various amplitudes, right, that you can kind of work with. In this video, what we want to do is we want to extrapolate of what we have learned in grade 11 on transforming functions in general. So any functions that we had, so any parent functions, for example, like the quadratic function, okay, the parent of that, or the cubic function, or the log function, or the exponential function, and so on. So all of those functions, we have noticed that if we wanted to transform them, right, we could scale, we could compress or stretch them, and then we can also translate them, right? So we can translate them up or down. And we've noticed that every parent function that we work with, the transformations that we apply basically yield the same results. So you have a compression or a stretch in the y direction, or a compression and a stretch in the x direction. And then you have a translation. So you're moving it to the right, to the left, or up and down, the various functions that we had. Now, in this video, we're going to be talking about transforming just the sine and cosine functions. And I'm going to be applying exactly what you have learned for transforming in the past. And hopefully, now that you've been seeing this over and over, the concept kind of starts to accumulate in your mind, and you're like, okay, I think I kind of get these transformations. And I'll show you some examples. I'm going to pop up Desmos, which is probably kind of my favorite tool. So thank you, Desmos, in terms of graphing these functions. And then we're going to take that Desmos and I'm going to show you, how these changes happen. So if you have, and I'm going to start off with just the sine function. So if you have your sine function, so let's say it's right there, and you wanted to transform that sine function. So our sine function, so it's this function f, okay, and our parent is sine of x. So here's our f. And now instead of just having sine of x, which we kind of know that it looks like, okay, like that, and it has a period of 2 pi, amplitude of 1, what would happen if we start playing around, okay, and start transforming? So what if we had, so for instance, what if we have this a in front, right? So what would happen? If we think back of transformations in general, well, what happened is that if we have a, so if we take the absolute value of a, and it is less than 1, we've noticed that basically what happened to our function, it just started to being compressed in the y, so it started to get squashed down. If our a was greater than 1, then it started to get stretched out, so it was pulled apart, okay, in this way. And then if a was negative, what we've noticed is that there was a reflection, okay, in the x. So the function, however it looked like, okay, it just kind of reflected in the x-axis. And we want to be able to see that if that's exactly what will happen with sine. And probably because you've now looked at many transformations, you'll be like, yeah, that's pretty much what will happen. You're correct, all right? So that's what our a has done. Now, inside, okay, so if we have sine of x, but now instead of having sine of x, we have now some particular d, okay, which is in front of this x minus h. So again, it's some kind of a scaling of some kind. And what we've noticed is if we plug this in, then d, whenever it is less than 1, that actually causes kind of the opposite of what happens in the y. So it causes not a compression, but it stretches things out. So it pulls the functions apart, okay, in this direction. And then if d is greater than 1, then what we've seen that it actually compresses it in. So it kind of compresses those functions inwards. And then if d was less than 0, so if it becomes negative, then all of a sudden we have a reflection in the y, so it just flips over, all right? And we've seen that with all the numerous parent functions that we've seen. Now, this h that we have right here, and then this k that we have, these were causing translations. So basically they would shift things over. So they would shift our function. So if h was positive, okay, so it would translate it to the right. Okay, if h is negative, it would translate it back to the left. And again, with k, okay, it would translate it up if it's positive and down if it's negative. And this is exactly what we would see right here. So in our sine functions, okay, that we have, what I'm going to do is I'm going to pop up Desmos, and I'm going to show you exactly and discuss these so that you can visually see these and you don't feel like it's something, you know, extraordinary. And then I'm going to take up a couple of examples where we're going to be sketching these things, right? So with this knowledge, can we actually sketch the sine, or can we sketch a cosine exactly based on these transformations? So here is kind of our Desmos. So I've prepared, and notice, so what I've done is, so on the left hand side, if you see it, okay, I have prepared our function, which is sine of x, but I've restricted it. So if you've used Desmos in the past, you can set restrictions. And notice I set the restriction between 0 and 2 pi. All right, so it's basically between that bounds. Actually, you know, what I can do is, you know, we'll make it less than or equal to here, okay, just so that we have the entire period, okay? So we know that that's the entire one cycle of our sine. And this is what I like to do with these transformations. I don't like to graph out, you know, for where the domain is basically all, okay, the actual x values. Now, please remember that x actually stands for the angle, right? Because sines are just ratios within a triangle. If you go back to the unit circle, right? So we're just trying to see what happens to that ratio as you keep swinging around. And I am using radians here, right? So, you know, you can define it in terms of degrees. I've kept it as radians so I can easily map it in Desmos. And for that, if you changed it to degrees, it would have been between 0 and 360 degrees so that you can make that full rotation. And then what we would see is, because it's a periodic function, it just keeps repeating, right? It just keeps repeating the same pattern over and over. But for me, what I have found is, if I allow it to repeat, right, and then I see this big sine function going to the negative side and positive side, then I find that my mind isn't very, you know, it's not very good at grasping the periods and these cycles continuously. When I have one, I can extrapolate, I can make more cycles after I do the transformations, right? Then it's much easier for me to see. So I like to restrict it to one period and then work on the transformations and then extrapolate, you know, for more periods if you wanted to. So for instance, so first off, so the blue that you see right on the screen, that's basically set as sine of x. And now what I'm going to do is I'm going to kind of work, okay, with the various values. So RA, which if you would be transforming, which happens in front of your sine, so if you would put that in front of your sine, okay, that should be changing, right? And what we said was, if A is greater than 1, it's going to start to kind of stretch these things out. If it's less than 1, okay, but greater than 0, it's going to try to compress it down. All right, so that's what we would try to see. Let's see if this is actually what will happen. So here's my A, okay, and I have done this in past videos in terms of these transformations. So notice, if I make A greater, let's say I made it to 2, notice that basically what it has done, it has just kind of stretched it out, right? So it's going to be stretching it out. If I go back into our notes, okay, within here, okay, so if A is, so the absolute value of A is greater than 1, notice that it just basically stretches out our functions. This is nothing new. This happens in all the transformations that you've studied of your parent functions, you know, from parabolas, okay, to logs, to exponentials, and so on, and now to sine. And also the same thing would happen to cosine. Okay, so if I keep going, it's going to just make it bigger and bigger. Now, if I make it, okay, so notice if I go now less than 1, now it starts to compress it down. So it's like it's changing its amplitude, So basically A in this case is kind of like your amplitude, right? So notice if I want to look at this peak right here is 0.6, that would be your amplitude. So not only is this a compression or stretch, it also tells you what the amplitude would be of our periodic sine function. And now if I flip it over, notice what was going to happen. If I make it negative, right? So what happens? What we said was if it's negative, then there is a reflection in the x-axis. And that's exactly what happens. The red that you see, that's your original sine function. That's just sine of x. And now here, your blue is basically the transformed function. So now it's negative. The amplitude is 0.8. And if I make it bigger, of course, it's going to make the amplitude bigger, right? It's going to try to stretch it out even further. So that's what has happened to A. Now let me bring A back. So I'm going to bring it back to 1, just so that we have our function back again. Now what about the D, right? So that D that we have in there, so what did we say about that? Well, if D, so I'm going to work now with D in here. If D is going to be now bigger than 1, what has that done in the past? It has kind of compressed in the X, okay? So it's like it's changing our period, right? It's going to change our period of this actual. So notice if I make it bigger, it's going to change the period, right? So let's say if I made it 2, so equal to 2, I'm going to put 2 in there. That basically would half the period. Originally it was 2 pi, that was the period, or 360 degrees. Now if you make D is equal to 2, it's going to make the period half of that, which is going to be just pi or 180 degrees. And now if we kind of allowed it to let it go, where we're now not just restricting it to one period, you would have noticed that this sine function would have just continued on with its cycles on and on. Now, what if, so if I go back here, if I make it even bigger, it's just going to continuously try to compress in the x, right? If I make it between 0 and 1, notice that it's going to start to stretch it out, okay? So it stretches it out. It stretches the period out. Now, if I make it negative, now I'm going to shift this over just so that you can see. If I make it negative, we want to see a reflection in the y. That's what we've always seen. And indeed, this is exactly what will happen. So notice here, okay, it just now reflected completely in the y. And then it either compresses or stretches depending on the absolute value, on the magnitude of that d. Now, let me return it back to 1. Now, what happens with the k and the h? Those ones are typically the easiest ones. The k just does a translation to the left or to the right. So notice if I make this, okay, be greater than 0, it's going to be shifting it to the right. If I make it negative, it's going to be shifting it to the left. So that's not a big deal. And the way you can think of it is because you're starting from 0, right, from 0 degrees or from 0 radians, just take that point and then shift it accordingly. So notice here it says it's negative 2.4. So that means that 0 is going to get shifted to negative 2.4, and so will every other point. Okay, that's your k. Now your h is basically going to translate it up or down. So here, notice this is exactly what we see. Okay, and it's going to be translating it up or down. I mean, if I bring this back, okay, to 0, and then I bring this back to 0, and I start making it larger, so it goes up or it goes down. And that's exactly what happens here. Now, is your cos function any different? No. Your cos function just looks a little bit different. So here, if I put cos instead of sine, I'm going to rewrite this as cos. So notice your cos, one period, looks like this, right? So now if I bring it back, because cos starts from 1, okay, and then it goes down and then comes back. So its period looks a little bit different. Okay, so that's how a cos looks like. And again, so if I play around with A, if I make it greater than 1, notice that it stretches it out. Okay, and if I make it less than 1, it just starts to compress it. If I make it negative, it starts to reflect it in the x. Okay, so that's exactly what will happen to this. Now with the D, it's the same thing. So now if I go to D, okay, it's going to compress it or stretch it and then reflect it depending on, okay, if it's positive or negative. So here, if it's negative, okay, now it starts, notice the whole thing reflects over, right, which is pretty neat, okay, to see. And then the K, right, it goes and shifts it to the right, to the left, and then up or down, okay, and this is exactly what you see. I love doing this because, you know, with Desmos in this tool, I wish this was the tool that was available when I was around, but now with something as powerful as this, you know, you can do these transformations and visually get a concept of these stretching, compressions, and so on. So if I come back to our notes and I give you an example, so here's our sine, right? So that's our original sine from basically 0 all the way to 2 pi or to 360 degrees. I kept this, okay, I just kind of took it out of Desmos. So that's how our sine looks like. And now if we wanted to take this sine, and for instance, I gave you this, right? Now let's try to see if we can replicate, okay, the transformations without using Desmos. Now we're going to check with Desmos. But here, let's take a look and see exactly what happens, right? So how is this transformation working? So first of all, you know, we can take a look at this. So this is basically your A. So this is your A, all right? Now, I've used the letter M in here because F, I'm just assuming, so we're going to assume that, you know, F of X is equal to your original parent function. So we want to see how this is transformed. So that is your, so this is basically your A. So it's -2. Now what will that mean? Well, the 2 is going to stretch out in the Y. The negative means it's going to reflect in the X. So it's going to flip it all over. All right. So that's what we would have seen there. Okay. And I'm going to do that in just a moment. And now this is your, so this is your original function, so F, okay? Now in here we have to be careful because as we choose, right? So we have to write it in the form of, okay, this is supposed to be D, X, you know, minus H, all right? So we have to take out that 3. So I'm going to factor out the 3 so it looks exactly like this, okay? So it's going to be looking like that. So this is going to be 3x. Now, we have a negative here, right? So, I mean, technically what it is, this is just negative of -3, because the negative and negatives would cancel. And then we have a shift, okay? This is going to be our K. So there we have it. That's our D. So our D is going to be 3. So what does that mean? It's going to compress it in. So it's going to compress, okay, that in. So the period is going to be shortened. Now this right here, this is going to be your H. And then this right here is going to be your K. Okay, so your K is -1. So let's try to graph this whole thing out. All right, so I'm going to try to do that, okay, within here. So let's plot it up. Kind of like this, and I'm going to do it one by one. So first take your A. So here's your A. Okay, here is your original. I'm going to kind of sketch it out. That's your sine function. I'm trying my best here. So that's up to here. I'm only going to do 1 period. You can extend beyond 1 period. Let's say if your teachers wanted to, right? But concentrate on 1 period because transforming 1 period is much easier, especially the stretching, compressing, and then shifting around. And then once you have that 1 period located, you can just repeat it, right? Over and over. So my A, so it's going to stretch this out a bit, okay? So that's going to look kind of like, so it's going to stretch it out. Okay, it's going to go like this, bring it down. Whoops, missed it there. Okay, and then come back. Okay, so kind of like that. So the amplitude has gotten bigger. But because of the negative, so this whole thing is going to flip, right? So it's going to just flip all the way around. So really, okay, what we will have, I'm going to just keep switching colors. So it's going to flip within here. So it's going to kind of look like that. Okay, so here it is. That's your flipped one. So that's the change. Okay, that's the -2. That's how it has looked like. So it has extended the amplitude up. Okay, and now it's also flipped it because of the negative. Now this 3 that we see right here, so this 3 right there that we have. So what does that mean? The 3 means it's going to kind of shrink the period. So now the way that you can think about it is the original one has a period of 2 pi or 360 degrees. That d, right, because it's going to compress it in, what you're doing with that d is you're actually just dividing, okay, this. And that's going to shrink your period. That's going to be your new period. So really, this is your d, okay, within here when it comes to these sines, sinusoidal functions, okay, sines and cosines. So now within that, what does that mean? Okay, that this is 120. So we basically kind of shrunk it, okay, or we've compressed it in by, you know, not only by a half, by a little bit more than a half. So now this, okay, so how am I going to do that? Okay, so it's going to be, now it is positive, so there's going to be no reflection, okay, but it's going to really compress it in. I don't know if I can manage this, but it's going to be something like this, okay, kind of like that. It's not the greatest, but this is what it's going to do. It's going to compress it in. Right? Now the period, so instead, so right here, this was 360 degrees or 2 pi, but now this has become 120 degrees, right? Or 2 pi over 3. That is your new period now. And then it just keeps repeating over and over. Okay? Now, next one, the h, so now it's going to be shifting this basically to the left by 3. Okay, so it's going to shift it this way. So this, you know what, let me try. I'm going to try to do that. I'm going to just go over this so that I have just kind of one, and then, okay. And now I'm going to try, take this. Okay, perfect. So now it goes, this is at 0, so now it's going to shift it over by 3. Okay, so it's going to shift this all the way over. So it's going to be somewhere over there. Okay, kind of shift it over and kind of looking like that. So that is the shift. And then also it's going to, because of the k, so notice that the k is -1. So that means it's going to take this and it's going to bring it down by -1. Okay, so I'm going to take this and bring it down by -1. So it's going to kind of look like that. All right. And that's the actual full transformation. So let's see, right? So if I pop up decimals in here, let's see if this is what we get. So it's -2, 3. Okay, so let's see if I can replicate this. So let's go back to our sine. And now our a, so this was -2. All right, notice so far so good. Notice the amplitude increased and then it was a reflection. Our d right here, so our d was 3. Okay, so notice compressed it in, and this point right here, hopefully it will maybe show it. Does it show? Let's see. Not exactly. Okay, I just wanted to show you that it's 120 degrees or 2 pi over 3. Okay, but that's okay. So that compressed it in. So that was that. Okay, that's my D. My, was it my K or my H? Let's see in here. Okay, did I flip them around? Let's take a look. H and K. It was H and then it was K. Okay, so let's see in here. H and K. Okay, so I have them flipped around in here. So this was kind of h. This won't really matter, okay? It still all follows the same thing. Okay, so my h was supposed to be -3. So notice it shifted it to the left. And then my k was supposed to be -1. Okay, perfect. And this is what it looks like. Now, if you wanted to draw out the entire thing, okay, so what I'm going to do is I'm going to block this out. Let's say we wanted to, graph the whole thing, which was -2 sine of, this was 3x plus 9, right, minus 1. Notice, okay? What we have done is we have just taken one period, right? Now, if I do this, it's going to just overlap the period, okay? So that's what we have in there, okay? So that's what you can do, once you're plotting this, you can extend these. So if I move this out, notice we just have one period, and then it just keeps repeating, right? Over and over. So you can do that, okay? And if you repeat it over, then that's what you will create. Perfect. All right. So now here is another example. Okay. And here is cos. Now for cos, okay, so let me remind you, I think I kind of put it in here. That's kind of how cos looks like, right? And here we have n of x, okay? So and now here we're going to try to transform this one. Okay, so how will we do that? So we have our, so in this case, our original. Now we're starting with cos of x, okay, which is this. So no different. And by the way, if you really want, okay, you can see that sine of x and cos of x, it's kind of just a translation by 90 degrees, okay, of sine or cos, and then you're going to come up with exactly the same thing, okay? And maybe I'll point that out shortly. So within here, so what do we have? So we have a, so this is my a, okay, so my function, so let's rewrite it. So cos, I'm going to take out that negative, so it's going to be -1 x minus 2. So I get my d plus 3. So this is your a, this is your d, this is your h, this is your k, okay? So what does that mean? So well, now I'm going to scale this by 3. So I'm going to stretch it out. So the amplitude changes to 3 instead of 1. So now if I would graph this out, so let's see if I can do that. So this is what we have. And because it's -d, I'm going to try to do it in this way. And hopefully I can replicate this. Okay, so here's our original, right? So our original kind of looks like this. Okay, so that's our cos. So this is 1, right? -1. Now, we're supposed to be scaling this by 3. So, what's going to happen is this is going to be scaled by 3. And maybe I drew it. Let me let me make it smaller just so that it, we can see it. Okay, so it's kind of like that, maybe. Okay, so more or less like that, 1, -1, approximately. Okay, and now this is going to get scaled. So how it's going to look like is, so this is going to be 3 times bigger. So it's going to be kind of like this, right? And then this peak is going to be at -3. So it's kind of looks like that, all right? So that was that A. So that was the stretch in the y. Now, this right here, so what's going to happen is this will be, now it's -1. So there is no compression or stretching, but there is a reflection in the y. So actually, this our new one, so it's kind of going to be, if it's reflected back, so it's going to reflect back kind of like this. I didn't draw this very well. Ooh. Okay, so, well, I'll do the best I can here. Kind of going to look like that. So that's the reflection. So the blue just gets reflected, right, along. Okay, so this is 3, this is still negative 3. Now we have, this is 2. So what does that mean? Now it's going to get shifted back. Okay, so it's going to get shifted in this direction. So if I take this, now it's going to get shifted in this direction. Okay, I don't know exactly where it's, I mean, I guess we can figure out where this was, right? This is going to be pi, which is 3, so it's kind of going to look more or less kind of like that, probably. Okay, that's the shift of 2, and then it's going to get shifted up by 3. So now this is going to get shifted up by 3. So it's going to be pretty much like that. It's going to, I guess, touch the x-axis because it's 3, because it was at negative 3, so if it gets shifted up by 3, that's what will happen. Let's take a look, all right? Let's take a look in Desmos to see if we more or less sketched it correctly. So now it's cos. Let me change this to cos. So that's our original. Let me bring these back, okay, all of them. Kind of back to the, okay, so this is what we have there. Now, our A was 3, all right, so there we have it. So there you go, it kind of blows up, gets stretched out. Our D was negative 1, so we want to see that reflection, boom, okay, so it reflects it back, okay, over, so we see that. Now, our H, so I have my H here, that was 2. So yeah, there we go. So that was the shift. And then this was, I guess, going up by 3. And there we have it. Okay, perfect. So if I go back in here, I mean, my sketch's not exactly, but that's exactly what we wanted to see, okay, on this one. Okay, so now, and finally, you know, the original was 3x minus x plus 2 plus 3. So let me, I'm going to kind of split the screen here. Okay, and I'm going to add this one. So n of x equals, and you'll see that it's going to overlap and just continue on with what it's doing there. So that was 3 cos of negative x plus 2 plus 3. Yeah, there we have it. So that's the full one that you have. So you can always extend, you know, if I close this one down, right? So you can always extend the one period and then just continue the period. And that's exactly, you know, if I do this, it just, that's what it overlaps that. So there you have it. Now, the last thing that I'll point out to you is that, you know, in all of this, cos really is just the transformation from sine, or vice versa. Okay, so if I, you know, if I would put in here, let me, okay, I'm going to remove this, but let's say, you know, if I started with sine, which looked like this, okay, and now I'm going to remove the restrictions there, just so that we have our sine. Okay, so that was that. Now let me in here, so instead of sine, okay, I'm going to put in cos, so g of x is equal to cos, okay, cos of x. So notice that they kind of look the same. It's almost like one legs the other. We call it leg, like it's, you know, lagging behind the other. So the black one that you see, that's the cos, right? And then the red one is the sine that you see. But really cos is just, okay, if you translate this, now what are we, if we wanted to match them up together, right? You know, this peak happens at 0, this peak happens at pi over 2. So, and pi over 2 is 90 degrees, right? So if I have my h, right, if you're thinking back of those transformations, like my a is 1, my d is 1, you know, I don't have a k, I'm not translating it up or down, but all I'm doing is I'm just trying to go back. Then you will notice that, hey, wait a minute, if I now put this as simply pi divided by 2, then it will just map exactly to sine, and that's true. So sine of x is equal to cosine of x minus 90 degrees, or pi over 2. Okay, so those ones are actually identical. So sines and cosines in terms of functions, they're just translations of each other. That's all. All right, so this is it. It's kind of a little bit of a lengthy video, and one of the last ones for grade 11 in terms of transformations. And by now, I think, you, depending, your teachers might use different constant variables. I use A, D, H, K. I mean, it doesn't matter, but the idea of compression, stretches, and translations is exactly the same for all of those parent functions you have done in the past. So I hope that now you have a good set of skills that you can use these and sketch them, and then understand what happens to them if you were graphing. Thanks for watching. See you in a future video. Bye, everybody.